Record. Cool. All right, now we're recording. So first off, I think the most important thing that some people are going to want are the homework answers. Did anyone not do the homework? I saw two people turned it in, but did anyone do it and not turn it in?
I didn't get to do it.
Alex, what about you?
I did most of it.
Okay. So I'll run through the answers real quick, and if anyone has questions on them, we can go through them. So question 1 was basically to draw a bunch of free body diagrams. So the first one was a book sitting on a table, so that's pretty simple. Let me know if you can see this or if you can't see this, by the way. Book sitting on a table. It's going to have a normal force going upward because of the table, and it's going to have its weight going downward. That one's pretty easy. B was a box being pushed up a ramp. So you have your applied force going up the ramp. You have your friction force going against that, against the movement. You have your weight force going straight down, and you have your normal force going out from the ramp. Okay. C was a car being crushed by a vertical car compactor. So that one I would have accepted 2 things for technically. First of all, it's going to have its weight, obviously. And then I would have accepted either normal force or applied force. Either one is fine with me because they're both correct technically. And then it has another force going down, which is applied force. And usually we write F1, F2 just so that we know what they are. So this is the area here where there could be a little bit of difference, but for the most part, that's what it is. And then the last one also kind of has 2 answers. It is they're like I guess like an acrobat or someone hanging from a pole. You could either have said, here's the pole, and here's the acrobat, right? And there is the weight force pulling the acrobat down, and then a normal force holding the acrobat up because his hands are on top of the pole, right? Another way you could have drawn that is you could say, here's the pole, and here's the acrobat. And I didn't really expect anyone to get this because I don't think you guys really know it yet, but he would have his weight force going down, and then he would actually have 2 tension forces holding him up, and those would have been those are technically his arms. But tension forces are like string or cable or anything that's like holding something up through tension, okay? So I guess we can do A, B, C, and D is both of these. Okay. So those are the answers to number 1. And then we'll do a new thing here. Number 2, I'm not going to do all the math and stuff for it, but basically, so Q2, the friction force equals 40 newtons, and the normal force equals 196 newtons. Q3, let's see, you were to find just both forces, yeah. So weight equaled 147 newtons, and the friction force was 78.94 newtons. There's a point there. And the normal force was 103.94 newtons. If you guys rounded up and just said 104, 79, and 147, those are okay as well. I think that's all on that one. Yes. And then Q4, which was probably the hardest one. So first you had to draw a free body diagram, and then you had to do all the equations of equilibrium. So the question was basically, there's an angry college student doing his finals, and he gets so angry at his textbook that he shoves it up against a wall and is holding it up against the wall with his arm at an exact 25-degree angle. So basically, we've got our wall here. We got our book. Here's the center of that book. So the book wants to fall because of its weight. So we got our weight. Its friction force is pointing upward because that's it's like being pulled down basically. So that's our friction force. We have our normal force coming straight out from the wall because the wall is pushing against the book. And then we have our applied force here, which is that college student. And this angle there between him and the wall, his arm and the wall, is 25 degrees. Let me know if any of you guys have problems seeing any of this, by the way. Okay, so if you have questions on this, let me know, but otherwise I'm just going to put the answers. So basically, F is 20.96, or 21 is fine. Normal force is 8.86, or 9 is fine for this. This one is far enough that I'd prefer you put the decimal point, but and then weight is 49, and friction is 30. And all of these are in newtons, okay? Are there any questions with those answers? Going to take your silence as a no. All right.
Yeah, none here.
Alrighty. So in that case, we're going to do today's lecture, which is moments and torque, which are both pretty funky words. Okay. So I don't know if this is going to let me do this. Oh, it did. That's cool. Yoink. There we go. All right, moments and torque. So basically what we're doing is similar to what we did last one, which was the equations of equilibrium, except for now we're going to go into 3 dimensions and we're going to start talking about things that rotate, okay? Things that, you know, move in circles and stuff like that. Also non-linear forces, which is what moments basically are. So still we're going to split up our work. We're still going to be working in our X, Y, and Z coordinates. We're not ever going to really be working outside of those for this. And remember that coordinates are your friend. You will need to change your coordinate system, as in like you may have something that's at an angle and it's better to just tilt your coordinate system to fit that angle. So make sure you're always using a coordinate system that makes sense. Angles are still difficult, so try to get rid of many as possible. That's what I was saying with tilting your coordinates. And then for the equations of equilibrium, we're going to be basically still in our X, Y, and Z components and still using Newton's three laws, but we're going to be specifically for moments and torque, mainly looking at this Z component for today. So moments. This is where it gets a little complicated. So we have a force, right? So here's like a little diagram of like a wrench. We have a force, that's our applied force F, right? A moment, what a moment is basically the equivalent of a rotational force, okay? It's a force being acted on some sort of pivot, some sort of thing that rotates at a certain distance. So torque, which is also basically what a moment is force times the distance perpendicular to that force, okay? Or you could say distance times the perpendicular force. This little kind of like upside down T, that means perpendicular. It means it's at a 90-degree angle, okay? So basically what this is, F is the applied force. That's the force that we're applying to something. So like if you're twisting a wrench, that's the force you're applying on the wrench. And D is the distance from the pivot to that force perpendicular, okay? So basically it's a way of simplifying things down to saying I'm pushing on this far away with this amount of force. That's going to cause this amount of rotation. So the way moments work, basically, because t or m, either one, moment or torque, depends on what you're doing, is force times distance. If force gets smaller, the moment gets smaller. If distance gets smaller, the moment gets smaller. If they both get bigger, the moment gets bigger. It's a direct relationship, but scaled. So basically, with this little diagram here, if we go the furthest distance out, right, that we can on this wrench, and we apply the force there, then we're going to have our maximum torque or a maximum moment. So the further out we are, the more it's going to want to twist this thing. If we go further in, like not quite to the edge, then we're going to have a smaller moment, a smaller amount of, I guess, twist factor. If you get pretty close, then you're going to have almost no moment or torque. And if you go straight onto the pivot, like if you like have a wrench on a bolt and you just grab the bolt and push forward, it's not going to twist, you know? It's just going to sit there or like stay in its hole because it's a bolt. And that's not how that works. So if you ever apply a force directly onto the pivot, the moment is going to be 0, which will be important when we start doing equations of equilibrium. So what that says basically at the bottom there, if d distance decreases, then torque will also decrease. And if it ever reaches the pivot, it will become 0. So that's important for later. Important thing to know, though, for moments is sort of what this diagram shows, which is even if you're pushing on something that is bent or like rotate or like has a bend in it like this, it still doesn't, you don't measure, say, this distance and then this distance and then this distance to find your distance. It's just from, and this is sort of XY coordinates, if up is Y and right is X, D would be on your X coordinate. But it's always just the distance from the pivot to the force perpendicular. It's never like, we're not going to do like an angle here. If we do an angle, then we're going to be splitting the force up into its components respective to that angle. But basically what this is saying is P here is the pivot, M here is the moment, D is the distance, F is the force. And so F times D equals M, and we would say M about P because it's around P, okay? But the important thing here is even if the thing that you're pushing on or putting a force on has a bend in it, it's still just this distance. So that's the general basics. Statics, the way we do this is the same way we did statics before. We still have like sum of F equals 0, or sum of Fy equals 0, which could be like two tension forces, let's say, or sum of F of X equals an applied force minus a friction force. You know, these are the things that we were doing last class. Sum of Fz, which is just in the z direction, is maybe like a normal force minus a weight force. Those are normal. And then down here is where we start to get into moments. So moments work the same way as forces do, where you say all of the moments added together equal 0 if we don't want our thing to move, right? And these weird sort of squiggly t's, like these curvy t's, these are called taus. So that's the Greek letter tau, and that's how we denote torque, okay? Because tension is a force, and then we want something else to be able to say torque, right? So we have to have something to be separate from tension and torque. So tau is for torque or moments. And we always do like a notation of like T1 is tension 1, T2 is tension 2, tau 1 and tau 2 are torque 1 and 2. So here's a like simple example, and we're gonna do this real quick because I think the best way to learn this is gonna be just doing it. So I'm gonna stop. Well, I'm not gonna stop sharing screen. I'm gonna move to a different screen. Boink. And shoot. All right. So did Cynthia leave? I don't see her there. Rip. Well, good thing this is recorded. All right. So I'm going to redraw this. So basically, we're going to say we've got our pivot, right? And then I guess I'll kind of draw the wrench. Yeah, wrench. That's a wrench. Okay. So we've got our force, which is 50 newtons. Why is this all wobbly? Am I on something? Yeah, I am. Oh, there she is. All right, so we've got our wrench here. We've got our pivot. We've got our force, which is 50 newtons. And then we've got our distance, which is 0.15 meters from our pivot, okay? So what that means, and we want to find the moment around P. So what we're going to do is we're going to say MP equals, and this is pretty easy because this is the simplest example I could think of, just F, which is this, times D, which is this. So we can say MP equals 50 times 0.15, which equals some number, which I'm just going to plug into a calculator. 7.5. And because I want to start using some units, because they're going to be useful later, we know that the force is in newtons and the distance is in meters. So we know that this is in Newton meters. So what we do there is we just write Newton times meters, and this is our answer. However, similarly to vectors, moments also have direction, but their direction is not like it's not like up, down, or to an angle. It's either clockwise or it's counterclockwise. And what we usually say is that, I mean, it depends. You can choose this, but usually we say counterclockwise is plus and clockwise is negative. I don't really know why. It's just kind of how it is. And you'll sometimes see these notated as CC or CW. So this is clockwise, and this is counterclockwise. Yeah, the right-hand rule. Yeah. What Kyler's doing is a thing called the right-hand rule, which is pretty useful. Basically, if you take your right hand, you can do a couple rules with it. You can either put it in sort of this configuration, and what this is one finger is, each finger is an axis. So you have like X, Y, X, Y, and Z. And then if you take your hand, which I have a drawing glove on right now, but if you take your hand and you like curve your fingers in the way that the moment is going, it'll point the direction on the axis that moment is about. So like, here, I'll draw this on the screen. If we have our coordinate system here, yeah, that's a okay coordinate system, where this is X, this is Y, and this is Z. Basically what this is like, if I have a moment going around Z, right? If I take my hand and I curve it the same way as that is, my thumb is pointing upward, which this is positive Z, like up is positive and down is minus. So basically, if you did your right hand rule, your thumb would be pointing up, and therefore counterclockwise is positive. And then if you did the opposite, you know, if you had that, and you flipped your hand over and tried to do the same thing so that it would be rotating the correct way, your thumb would end up pointing down. So right hand rule is pretty useful. I tried. There we go. That's a hand. So that's the notation. The thing is, when you're doing statics, you can choose this if you want to. You could say that this is positive and this is negative, as long as you keep that for the entire time that you're doing the problem. If you ever change, you're going to be in some troubles. But if you keep it the same, you can kind of choose. However, the standard is to use, whoopsie. The standard is to use that clockwise is negative and counterclockwise is positive. So I would suggest that you stick to this because it'll be easier. Okay, so that was the simplest example I had, just to kind of show you what a moment is. And because that's already kind of a thing. Yep. Because that's already kind of a thing, does anyone have any questions about just moments in general? What moments are and how they work? No? Okay. So now we're going to do a different example. So if you want, you can go ahead and kind of like write this down real quick. I am going to redraw it though, because I'm going to do it. Actually, I think I can draw on here, can't I? Yeah, I can. Annotate. Nice. Okay. So this is another problem. But basically, this is showing what I was explaining earlier about how a bint item can still, you can still do the same calculation. So we'll call this P, and we're going to say moment P equals the sum of all moments around P, okay? And basically what we're going to say there is that here's a force over here, here's a distance, and there's another distance, and then the y component, we'll say. So, and this is MP. So basically what we're going to do is we're going to do MP equals force times, and we'll call this D1, and we'll call this D2, and we'll call this D3. So we know that force times D1 plus D2 equals the first moment, right? Because this is the distance here, D1 plus D2, times its perpendicular force. So we know that this equals 20 times 8 plus 10. And then we know that the force in the y, so like right here, what's going to be perpendicular to this distance is F equals 0, because there's no force applied in that direction. But we still need to do it because it's still technically there. I mean, you don't have to do this when you're actually solving problems, but for explanation's sake, I'm going to go ahead and write it. So we'll call this F2 and this one F1. So basically, we'd also say plus 9 times F2, which would be plus 9 times 0, so it cancels out. This term doesn't exist. And then we end up with 20 times 18, which is, what is that? 6 to 36, that 360. So 360, and we've got pounds here, and we've got inches here, so we're going to say that's inch pounds, because that's a thing. And that equals MP. One problem with this is I do not have a lot of space. So Cynthia, are you doing okay there? You keep dropping.
Sorry, it was glitching a lot, and whenever you were talking, and it kept like rebooting and like going off and then on. So I switched to my tablet.
Okay. Here, let me see if I can. We'll see if this dips. Can you guys hear me? Okay.
Yeah.
Swapped to a different network, hoping it would be better just in case. All right, cool. Okay, so I guess for those that heard, does this example make sense? Yes. I guess a better question is, are there any questions about this example? Nope. Okay. In that case, we will move on. Oop, I'm gonna need to clear that. Is it gonna let me clear that is the real question. There we go. Clear. Clear all. Cool. Okay. So the next thing is just a real quick mention of joints and links, because they're, when we do, like, when we start actually analyzing some stuff, they're going to be important. Basically, there's some different types of joints and links. So like if I have a beam, let's say part of a building, right? Yeah, we'll say a building. So if I have like a building, I can't draw because I don't have annotations on. If I have a building here, and it needs a flag or something coming out of it, right? Like just like a little flag. The flag in this case, we're just gonna say has been like implanted into the building, okay? Like the rod for the flag. That would be an example of a fixed joint, because it's like it has no way to move. And what a fixed joint does is, when you have a fixed joint, it's completely static and completely defined. So what that means is it has a y component force, a x component force, and it has a moment about it. So what that means basically is this joint, but the rock around this joint doesn't want it to move in the y, x direction, and it doesn't want to let it twist, okay? It's holding it in place. Come on. Another version of something is like, let's say we had a, let's say we have a cliff, and we just put like a board across that cliff, okay? Because we want to get across it, but we don't have anything. Basically, the edge of the cliff here and here is going to be supporting the board. So it's going to be applying a normal force is what it is, but this is called a just a simple joint. It means it's just something sitting on something else. And it only applies a force in the y direction, or depending on where it is, like we could say instead this board was like up against a wall, in which case it would be applying a force in the x direction. But basically it's just something is butting up against something else, so it's only really constraining it in one direction. So that's a simple joint. A roller joint is like, say we have a wheelbarrow. That's a wheelbarrow. And it's on a roller. A roller joint also only applies a f direction force, or a singular direction force. So like if it's on the ground, it'd probably be f of y. But the interesting things about rollers is they're always, and simples can be like this, but usually aren't. Rollers are a singular point force. So like if I've got like a ramp here, and I've got a roller joint, and then I have a board on it, right? If I had this board just laying on this ramp, the ramp would be applying a normal force like this, right? But since it's on a roller joint, it's actually just a force going up straight out the roller, because that's where the force is being applied. If you looked at the ball itself, there would be a normal force going this way. but that, I mean, we're not looking at the ball, we're looking at the board. So roller joints sometimes simplify stuff. And we also are going to be using roller joints because wheels are roller joints. A pinned joint, and the way we note a pin joint is like if we have a beam or something, we write a pin joint as if it's like a little triangle, and then whatever the triangle is connected to is usually static, and these lines here mean it's static, it can't move. A pin joint is basically like if you have a beam and something is like literally pinned to it, okay? Like there's a pin going through it. And a pin joint applies a y direction force and it applies an f direction or an x direction force. However, it does not apply a moment, okay? Basically what that means is if I try to push this beam upward, this pin would keep it from going up, right? If I tried to push it to the right, this pin would keep it from going to the right. But if I wanted to rotate this beam around the pin would let you do that because it's a cylindrical pin. So it's like a hinge. The reason these are important is when we start looking at actual systems, we're gonna start using some of these. So like if we have a robot, right, and it's got wheels, the wheels here are both roller joints. So we know that we can just put single forces on them. However, if we have a robot and we're looking inside the robot and we have an arm here that's pinned to the robot, we know that the arm is going to have a y direction force here and an x direction force here. So when we start doing our equations of equilibrium, this is going to be important because we have to put these in our equations because we know that they're there. We just may not know what exactly they are yet. So yeah, that's just a quick explanation of joints. Okay, so here's a problem. There's a little robot boy here. So this is what this is going to be a little bit more complicated, not a ton more complicated, but a bit more. And basically what it's going to be is just looking at this as a system. We are going to treat the robot not as a single point, but we're going to treat it as its whole body. And we're going to be applying forces where they're actually applied, okay? So we need to first look at our word problem up here and choose what in it is important. So we know that the robot sits on the ground. That's important. We know that it weighs 15 newtons and that is at the robot's center. We know that it has an arm with a 5 Newton claw on the end. We know that its wheels are 0.2 meters apart from each other. And we know what we're trying to find is how long the arm can be without the robot falling over, okay? So what we can say then is we can say weight equals 15 newtons. We can say that we'll say W2 for the weight of the claw equals 5 newtons. We'll put a 1 here. We'll say that D1 equals 0.2, and we'll say that D1 is the distance between the wheels here. And then we know that D2, which we're going to measure from this wheel to keep things kind of simple, D2 is the length of the arm that we want, okay? So, oh, and then we'll go ahead and put a center of mass, and we'll say that this is where weight is, and weight 1, and then we'll say over here is where weight 2 is. Okay. Alrighty. So that's our real quick diagram. Can anyone tell me what the first step is to finding out what D2 needs to be? I will wait here all day. Alex,
Yes.
what's the first step? If you get it wrong, that's totally chill. Just, I'd like you guys to say some things. Whoopsie.
I have an idea of how I would do it,
Okay.
but that's cheating because I know this stuff.
Yeah, I was gonna say. I feel like yeah, you would have an idea.
So would we establish a torque or a moment?
Yeah, so we can. So we can say, and actually, I guess first things first, we should say our coordinate system here. So we'll say this is y, and this is x, and this might be a little hard to visualize, but z is actually pointing in and out of the page. Like if we had our coordinate system here, like this, right? And this is x, and this is y, and this is z. We'd be looking straight downward on z. Okay. That's how we're gonna do this coordinate system. So z is like in and out of the page. Out of the page is going to be positive, and into the page is going to be negative. So the way we usually write that is out of the page is a circle with a dot in it, and into the page is a circle with an X in it. And the way I like to think about that is it's like this is the point, if like this were an arrow pointing in and out, right? The arrow is like a little circle, like it's got like a cone tip, and the back of it has an X on it. And so when we're looking dead at the head of the arrow, we're looking at the point of the arrow. And then when we're looking at the back of the arrow, we can see the X on the back. So that's kind of like how I like to visualize it, but that's up to you. But coordinate system, yes. So moments, we are going to establish at least that there is, that the moments are going to be there, right? So we'll say the sum of in, and what axis are we going to be looking at?
P.
Huh?
P, right?
Here are our three axes.
Oh,
Would it be Z?
It would be z. So basically, like if something's rotating, right, it will be rotating about the z-axis. It'll be rotating around the z-axis. So yes, we would be moments on the z-axis, and we can say these equal 0 because we don't want the robot to move, right? We don't want it to tip over. Specifically, is what we're looking at is when it does not tip over. And by putting it at 0, we know it's like, if we want to, we can put it right on the tipping point. So moments about the z-axis equal 0. And I'll put it equals here, but we're not going to fill that in quite yet. What else do we need to write? What else do we need to establish?
We would need weight 1 and weight 2 somewhere in the equation. Or would it
Yeah.
be weight 1 minus weight 2? Because
Well,
weight
first,
1 is
so we
supporting.
have our moment equation, right? Or like we have that, we're going to have a moment equation. What other equations are we going to have, I should say? So to be clear here, when we're doing statics, so I guess statics, all it means is nothing moves, okay? That means nothing twists, which is what the moments are. Wow, that was a really bad arrow. So nothing twists, that's our moments. Nothing moves to the right or left, that's our x. And nothing moves up or down, which is our y. And if we're looking at a three-dimensional space, nothing moves back or forth, which is our z. Okay? So we need an equation for all of these, except for right now we don't need a linear z because we don't have any linear z components, okay? So What is another equation we need?
Sum of all x.
And I'm gonna go ahead and get rid of this because I'm gonna need the space. And there we go. Okay, so yes, sum of all forces in the x equals 0. And then what else? It's one more.
Sum of all y equals 0.
Yep. Alrighty. So we have our three equations. And those are all going to be important here in a sec. However, this diagram that we have here is missing just a couple of things. Can anyone tell me what they are? I'll tell you there are a couple of forces.
We
Natural
would need
force.
the normal force for the body of the robot.
And
Counteracting weight 1.
where would the normal force be?
Through the
Pointing
holes.
upward from the center of mass.
So,
Acted on weight
in this
1.
case, no. Yes, there are going to be normal forces. No, as to where they're going to be. So when we're looking at moments specifically, we need to put forces where they're actually being applied. The part of the robot that is touching the ground is its wheels, right? So our normal forces are actually going to be applied at our wheels. And there we go. So we can say that this is in 1 and this is in 2. Okay. Now, later on, we could simplify these into a single normal force and put it here and just call it in. However, because of moments, because we need to know the moments, we can't do that right now. And we are going to need them at these locations. Okay. So we got our normal forces. So now that we have all of our things in our diagram, we can go ahead and write out some of these equations. So would someone like to pick an equation and write a bit of it out? I'll start calling on people if no one answers.
So in sum of all y equals 0, we would have normal 1 plus normal 2 minus weight 1.
Yep.
And then minus weight 2 also.
Mhm. Perfect. Okay.
For sum of all x is equal to 0, is it force minus friction?
So there's so when we have a box that we're pushing along, right? Pushing along a surface, we're pushing it so there's an F, and because it's on a surface and we didn't say that there's no friction, there's a friction force, right? In this case, the robot's just sitting still and no one's pushing it, and it's just sort of sitting there. So there's no, if you look at the diagram, like we look at all of our different forces here, right? Are any of them working in the X direction?
Oh,
No, they are not. So we can actually just say it equals 0 because there's nothing there. Which is important to know though. So, and that's why I kept this equation in. It being equal to 0 is actually kind of important. Especially just for knowing how to write these equations. Okay, so we've got our f of y, we've got our f of x. Now let's write our moments. Does anyone, and this is a trick question because none of you are going to know the answer, but I want to see if you can guess. Does anyone know what the first step is for finding our moments about z? Other than Kyler. I'm gonna, how about this? Kyler, go ahead.
Okay, well, I would probably start by defining where you're finding the moment about,
Yep, so we gotta
like
choose a
where your
point.
pivot point is.
Yeah, so you know earlier when I asked what the axis is and you said P, P just means pivot. which just means a thing that rotates, right? So we know that we're working in the z-axis, but we do need to choose a pivot. And what we're going to choose the pivot as, and I'll do it in red. We're just going to choose one of these wheels. Which wheel do you want?
N1.
Can anyone tell me why I chose one of the wheels?
Because whenever the robot falls over, it's gonna be
It's actually not why I chose a wheel.
They're roller joints, and they're each a single point force.
Closer. So, what values do I know numerically? Like, what values do I have actual numbers for?
The two weight forces and the distance between the wheels.
Yes. So, out of all of my forces, N1, N2, W1, W2, right? I have three of those, or sorry, two of those. We have the two W's, right? So we have this one and we have this one, okay? So what would happen if I put the pivot here when I tried to write the moment equation? In fact, we're going to say red is a bad pivot and blue is a good pivot.
You would be putting the force directly on the pivot, so it would equal 0.
Exactly. So what we would end up with was we would say that mz of p, which p is the pivot, would equal basically W2 times some distance minus N1 times some distance, and then plus N2 times some distance, right? And then we could fill in W2, so this would end up being a number. But then we have two unknowns here that could be different values, and so we can't solve it. So we just hurt ourselves pretty bad there. So what's smarter to do, so that you can basically take out one of the unknowns, to choose a good pivot point, which is one of the wheels. Because if we choose one of the wheels, the force that's acting on that wheel is going to be acting straight through the pivot, and therefore is going to equal 0, and we can just throw it out, pretend it doesn't exist. So what is our moment about P going to equal? And P is our blue pivot here. Alex.
W2 times D2.
W2 times D2. Yeah, and is that positive or negative?
Positive.
Yep. And then what else?
Minus D1 times W1. Or W1 minus D1 times.
So D1 is from here, like this line to this line, right? And W1 is halfway between them. So it would
half of
be,
D1.
and is it positive or negative?
Negative.
Yep, so we can say minus W1 times D1 over 2. Oof, that's small. Okay, and then there's one more. Anyone?
Would it be plus N2 times D1?
Yep. There you go. All right, so we have our two equations. Perfect. And what's great about this is now it's super easy to solve because we got these over here. And look, we got D1 too. Awesome. However, we don't have D2, which kind of makes things bad, but not that bad because we have this equation. Okay, so what we're gonna do is we're basically gonna write all our numbers in to see what we're left with, and we're gonna do the same down here, and then we're gonna try to solve this. So W2 equals 5 newtons times D2, which is what we're looking for, minus 15 newtons times 0.1, because that's 0.2 divided by 2, plus in 2 times 0.2. Ugh, that was gross. 0.2. There we go. Equals mzp. And then we can say fy equals n1 plus n2 minus 15 minus 5. Is that all right? Yes. I'm wondering if I actually shafted myself here with my problem, but we'll see. So we can go ahead and say n1 equals, what is that? 10? Yeah, 10 minus n2. So that's just reordering this equation because we know that this whole thing equals to 0. So I'm just combining these two. Oops, that should be a 20 because they're both negative. There we go. Combining these two because they're both negatives, and then we're flopping them over to the other side. So 20 minus n2. Here, let's see, we've got 2. I think I might have shafted myself with this question.
Yeah, the thing that I'm thinking
Yeah,
about
because
this.
here's the thing. We've got, so, well, the way I know that I did actually is also kind of important. And I'll just throw in another known so that we can solve it. But is, you see how we have 2 equations here that we have some values for, but we have 3 unknown variables. So anytime you're doing algebra, or number of unknowns variables must equal your number of equations. Yeah. If this is not true, or it can also be greater than if you have more equations than unknowns. So, or more. If this is not true, if you have fewer equations than you have unknowns, then the problem becomes unsolvable, unless you find some other unknown, or find another variable. So what I'm going to do...
The way that I would think about this is that technically, if you want to find the longest possible arm, that's technically the point where the center of gravity is directly above n1. So the normal force at n2 should be 0. Technically.
Yes. Actually, that's actually a very good point.
But then if you move at all, you will tip.
No, but here's the thing. This is silly of me. That's why I wrote this sentence here.
Yeah.
I did this yesterday, so I didn't remember the problem completely. So this is a trip between all of us. But no, yeah, what Kyler just said is actually very true, and actually used in robotics a lot. And that's why I wrote that sentence the way I did right here. Is because he is correct that if the robot is on the verge of tipping, right? So like if we know that it's static, it's not moving, but if this arm was any amount longer, even a 0.1 millionth of a 1 or something longer, then it would tip, right? We can say that n2 is 0 because this wheel no longer has any force on it because it's about to tip over. Which does make the problem solvable, which is, yeah, okay. I didn't think I made this problem wrong, but I started to question myself there. So so basically finishing it up, into here, we can say is 0. So we can say in1 equals 20 newtons. And then we can take this 20 newtons here, and we can plug it into this top equation. And we can say, I'm going to like put it over here, that 5 times d2 minus 15 times 0.1 is going to be 1.5. So we'll just write 1.5 minus 1.5 plus 0, because in2 is 0, equals 0, because all the moments add up to 0. Yeah, I mean, that makes this way better. We can now say that 5 times d2 equals 1.5, and then we can just say that d2 equals 1.5 meters divided by 5, which is 0.3. I was about to do that on a calculator. I don't know why. So we know that our arm, at its very maximum, can be 0.3 meters long, and we know that when that happens, we'll have 20 newtons on our front wheel, which is actually important sometimes, because if you have a wheel that's going to break under 20 newtons, you know that you cannot be doing this. So, and it's also specifically for FTC and robotics, you know that this value here, this 0.3 meters, is your absolute maximum, right? And that's only if your robot's staying still. If your robot's
if your
moving,
arm is that long and you move
Yeah.
at all, you will tip.
yes. So if you're moving, you will 100% tip over if you go forward. So what you know is that your arm has to be less than 0.3 meters. And usually what we call that, and I'm very much running out of room here, but usually what we say is we say a safety factor. So we'll say like SF, safety factor, equals 2. And what that means is basically the arm that we would allow ourselves to have as a maximum would be 0.15, because that's half of 3. So what you do is you take your maximum thing, which is 0.3 meters, and you divide it by your safety factor, and that will spit out your new maximum. Okay? So basically, what that's saying is like, you're trying to guard against the worst case scenario, you know? Falling over in this case would be the worst case scenario. You know, if you do 0.3 meters, you're gonna fall over. In other cases, it might be like, you don't want your motor to explode, so you put a safety factor on there. Or maybe you don't want your beam to break, so you put a safety factor on there. Those sorts of things. So this is a lot of writing, and a lot of things that just happened, especially because I confused myself. Are there any questions?
None here.
Alex, you got any?
No.
Okay. In that case, we will clear all. Oh, look at him smiling. He's so happy. And we'll go ahead and go to the next one. Now, here's a doozy. Not actually. This is actually a pretty easy problem. It looks weird and difficult, but it's not that bad. So we solved this the exact same way that we solved the other problem. But in this case, we're doing moments in multiple places. Last time we only did one moment. It was around the front wheel. Now we have a moment here, and we're going to have a moment here. And theoretically, we could have a moment here, but we're not going to do it. Luckily, this is a pin joint, so we don't have to say there's already a moment here, but we could take the moment around that point. Okay, and so let's go ahead and go through the problem and see first what it's asking us to do. So first, it wants us to draw a free body diagram of the member, which is AB, this whole thing. It's supported by a roller at A and a pin at B. And it says to explain the significance of each force on the diagram, which we're actually not going to be doing really explaining the significance of each force, but we are going to be finding the forces that aren't found yet, okay? So we know that there's a moment here and we know there's a force here, but we do know that there are two forces here and a force here that we don't know yet, okay? And if I need to, because this is not necessarily what the problem is for, I might add in a thing, but we should be able to solve this. Oh, hey, Cynthia, you're back. Does anyone know what the first step is? Other than Kyler, anyone know what the first step is? There's only 3 of you. It makes it calling you out very easy. Cynthia, you there?
Sorry, I was still drawing it. The first step would be writing the equations for f of x and f of y, and equate them to 0.
Oh yeah, that we'll say that's we'll do some setup here. We'll do f of x, f of y. We'll equal them to 0. Another important first step to literally any problem ever is to make sure you define your coordinates. So we'll do that over here. We'll just say y and x normal coordinates. What's the other one we need to define? Anyone?
Z,
Huh?
Z.
There's no z. What in z? Oh, are you saying the coordinate? Yeah. Sorry, I should have written that. What other equation do we need to define? What is this class about? This specific lecture?
Moments.
There you go. Moments in z equal 0. All right. So this one we do actually have x, y, and moment z components. So who wants to finish the free body diagram? There's only 3 things that need to be added to it. Anyone? Cynthia? You there?
Yeah.
Would you like to add one of the things to this free body diagram?
I don't
Eh.
know what I would add.
I know it's a little spooky, but here, I'll give you some hints. We've got a joint here, and we have a joint here, and they're going to be doing some forces. Okay? Can you tell me one of the forces that this joint will do?
I'm not for sure.
Okay. How about Alex? You want to?
Yeah, what about normal forces?
Yeah, so there'd be a normal force, which we're actually, because this is a joint, like a pin joint, we're just going to call it F. We're just going to call it a force. But yes, there would be a normal force coming from B. And what we'll call that is we're going to say F of B of Y. And I know that's a little weird, but it is a force that is on B, and it is in the Y direction. Okay. What's another one?
Wouldn't there also be FBX because pin joint has X and Y forces?
Yes, there would. So FB of X. Okay, and there's one more force that needs to get added to this diagram.
There'd be FA of Y because the roller joint has one single point force perpendicular to the connected piece.
Yes. In fact, in this case, it's It's a little weird. Because, so I'm gonna draw this. Let's say we have, I think I did a little bit bad job of explaining this earlier is why. So we have a roller joint where it's like a ball, right? And it's on a ramp. In this case, there's a force being applied like this, right? And then transferring through the ball, it goes up, right? In this case, there's actually a roller that is connected to the beam here. And so when we apply our force, it's because of where the roller is. Because it's the center of the roller is where the beam is, that force is actually going to apply straight through. Okay? It's kind of like, so if the beam was up here, right? This force would not be applying straight through. It'd be applying to the center, and then the center would be applying the force outward, right? But because it's right at the center of the beam, it's applying it straight through. So this is going to be at an angle, okay? It's kind of like, and I'll draw it up here. It's if we have a ball, right? And there's a force being applied to this ball, like this. It's going to apply that force to the center of the ball, okay? And then that center of the ball is going to apply forces to other things touching the ball. So if there's something on top of the ball, it's going to apply a force to that thing. If there's a thing, well, that's a bad area. If there's a thing over here, it'll apply a force to that thing on the edge of the ball. But if there is something on the center of the ball, it's going to apply straight through, okay? Does that make sense to everyone? Yeah?
Yes.
So there is a force here. It is a normal force being applied straight through perpendicularly to this plane. And we are going to call it F of A. All right. Now, the interesting thing about this is that means we have an F of A, a couple of F of A components. So we're going to have F of AY and F of AX. All right. Because we're going to split this thing up once we, I mean, we could split it up right now, but either way. Okay, so we've got our free body diagram. It's looking pretty neat, pretty good. So now we're going to start writing up here our equations of equilibrium. So can anyone tell me what we're going to write in the F of X category? Let's swap back to black.
It would be 5 minus FA of X and FB of X.
So not quite. So first of all, this 5 here, I know this is probably a little confusing looking here. That's just the ratio of the triangle. It's saying it's a 13, 12, 5 triangle. But the actual magnitude of that force is 390. So it would be, if you're trying to find a side, you're going to do triangle ratios, which is you do basically the hypotenuse here is 390 degrees or 390 pounds, but it's got a ratio like this. So if I wanted to find this side of the triangle, the X side of the triangle, I would do 390 divided by 13 times 5. Okay. Does that make sense?
Yeah. So it would be 150.
I don't know if that's actually what it is. Like I didn't.
Because it'd be
Probably yes.
times 30.
Yeah, that's right. Sure. And then one other thing is that we did define our coordinates over here, and positive X is pointing to the right. Okay. So just your signs were backwards, but other than that, all good. So we will do FA of X. Oops, I do. And then plus FB of X minus 150. Cool. And then what is our f of y? Alex.
It's kind of the same thing, but instead of x, it's y, and instead of times 5, it's times 12. Whenever we're finding what the
Yes.
390 pound thing
It'd be
is.
there. I'm just gonna do that so we have them there. Yes, so we would have fa of y plus fb of y minus 360. Okay. And then what is our moments? What's our first step of doing moments?
We have to define the pivot.
Where should we define the pivot? There is a very good place to define the pivot on this one.
Would it be at the pinned joint or at the pivot that's already defined?
No, it would be at the pinned joint for sure. Reason being, words. You could also do it at here. That's fine. The only thing is that if you do it here, these are both 0. It's just nicer. And moment, one of the nice things about it is if you have a moment, it's just a moment. You can split it up if you want to. So it's kind of a decision, I guess. You can, both are valid. If you want to find these forces first and then do moment stuff, you can. If you want to instead do moment stuff and basically ignore these and split this into a thing, you can also do that. Either way kind of works. And the way you split a moment up is you're defining a point, right? So you're saying P is here. And this moment, you know, has, it's 800 pounds. So you could say, like, if this was your P, right, there would be a force acting over here that is some force X, and then this D is some distance D. So you'd say that 800 equals F times D. That should be an 800, but whatever. And then you could find these, but what's nice about that is if you notice, there we go. We'd be then putting a force here for this pivot here, which is a big 0. So, okie doke. So, yeah, we can define a pivot P, and then I guess I'll ask, do you guys, I guess we should probably find these first. We have 2 equations, 4 unknowns, so nope, so moments. So let's write out our moment equation. And I guess, who wants to do that? Who wants to do the moments? No one wants to do the moments. No one at all? Someone's got to want to do the moments.
Just as a clarification here, you're not accounting for the thickness of the board, right? With
No, no, we're not.
that force there.
We are
diagonal.
assuming, no, we're assuming that the board is a single line. So no thickness.
Cool, cool.
Okay. I guess Alex, you wanna take a stab at this problem here?
So
I know it's a little wacky, but wrong answers are fine as well.
yeah,
So like, you know, whatever you can get.
is it 390?
If I didn't make this clear earlier, we do want to split it into its x and y components because those are going to be perpendicular forces. Okay.
So would it be 150 times 3 feet, or 150 at 3 feet?
Yes, it would. So, and is it positive or negative?
It would be positive.
Okay, so 150 times 3. That is one of them. What else? Anyone?
Would it be 360 times 12?
360 times, not quite. So yes, this distance here added up is 12, but this is being applied, the 360 is being applied here. And our pivot is here, right?
Yeah, one thing, the way that my structures teacher explained it is that if you imagine the line of action
Yes.
like extending infinitely, then you need to find a perpendicular line from that line of action to the pivot point, and that's your distance. So like if your force is in line with the pivot point, like if you extended the force infinitely and it crosses through the pivot point, then what's the distance going to be?
Where did my mouse go?
So would it then be FA of y at 12 feet?
Yes, it would. And positive or negative?
Negative.
Okay. And we are missing one more force. Alex, you want to try to get that last force? Alex, you there?
Yeah.
Would you like to try to get the last force?
No.
It's got to be a force where
I like
if
that.
you
No.
no, imagine extending kind of all of the forces that we've
Yeah.
drawn out
So
infinitely.
you see how there's FA here, or FA of y here. There's FAX here. There's we'll just say whatever we want to call. We'll just call this FC. So FC of y here and FC of x here, right? So FC of y goes straight through the pivot. So it's not gonna account for moments. These two down here are on the pivot, so they're obviously not gonna account for moments. FC of y, which is that 150, it does not pass through the pivot. And if we draw a line coming out of the pivot, we can see it's perpendicular, so that works. So we do one for that, which we've done, which is that 150 times 3 here. There we go. And then over here, we've got two other forces. If we draw that one, keep going, it does not pass through the pivot, so we need one for that. We draw this one, keep going. It does not pass through the pivot, so we need one for that. Okay? So all these forces, if you just made them super long in whatever direction they're pointing in, and they don't pass through the pivot, if that happens, we're going to need to do to put them into the moment equation, okay? So which one of these forces do we not have in our moment equation, but does not pass through the pivot point that we've chosen? Sorry.
F
what is it?
of X.
Yes, the FA of X. Which, if we're putting it in moment, is multiplied by what? So I'll go ahead and do, I'll give you that it is minus FA of X times thing. What distance?
Is it also 12?
It is not 12 because FA of X is pointing in the X direction, and this
Oh.
12 is also in the X direction. It needs to be something in the Y direction.
3.
Yes, 3. So we'll put our 3. Cool. Sorry, my nose is super itchy right now. I don't know if you guys have had this similar problems, but allergies have been very bad lately, and I have not been a fan. Okay, perfect. So we've got our forces here. There is a moment here. That was a lot of circles. So, God, my nose. When we are doing moments, something interesting about them is it kind of doesn't, it's going to be kind of weird saying, but it doesn't matter where they are. So like, sorry, one sec. Yeah? I'm teaching class, bud. In 30-ish minutes. I love family. Okay, sorry about that. So like I was describing earlier, that completely destroyed my train of thought. We have a distance d, and I'm trying to remember if I'm completely justified in saying what I'm about to say. And I think I am, but I want to double check. Kyler, you can correct me if I'm wrong, I guess. Is basically moments don't matter where they are, in the sense that if we're taking the moment about a pivot P here and we have a moment over here, we can split it up and then reapply it. And what that would be is like, we'll say, I'm actually not going to apply it there. I'm going to apply it over here. Yeah, that works. So because this is 8 feet and this is 800, we can reapply that as a force over here. I know that's right. I don't know why. Yeah. So basically what we're saying is 8 feet here is our distance, right? And 800 foot-pounds is our moment. So we can say instead of this moment here, we can basically convert it into a force and then reapply it at our pivot point. So we're going to go ahead and do that. And so we're going to do 800 divided by 8 equals 100. And we know that that is going to be applied over here perpendicular, right? So we have an 100-pound or a 100-pound force.
That's going to go down.
Oh, you're right. Sorry, it is down.
Yep.
100-pound force pointing straight down over here. There we go. Because if we drew a line out from this pivot point, that's what's perpendicular. Okay. So basically, I'm just taking this moment and splitting it into its distance and force, and then now that I have a force over here, I can reapply it to our pivot point, which is P. And the way I'm going to do that is I'm going to say the distance here is 12, and we have an 100-pound force that is 12 feet away. So I can now say, and this is counterclockwise, so it's positive, I can say 100 times 12. So that is our, basically we're taking this and we're converting it into that, okay? Does that make sense to everyone? I think it does. So, okay. So, I don't have a ton of room here, so I might have to start deleting things, but that's okay. Let's go ahead and simplify this equation real quick, just so it's not so oobly goobly. And what that's going to be is just like 50, we're just going to combine the numbers basically. So we've got 450 plus 1200. So we can convert turn that into 1650, and then minus this stuff up here. So I'm just going to rewrite it because I am running out of space. Hardcore. Minus fa of y, 12 minus fa of x, 3. All right, so now let's see how many equations we have and how many variables we have. We've got basically our 3 equations here, and we have 1, 2, 3, 4. Is that right? Did I get all those? Looks like I did.
You could just write another equation that's just the relationship between FAY and FAX.
No, yeah, that's what we're going to do, but I wanted to make sure that I got all the variables there. I did. Cool. All right. So now, and is Cynthia here? Yeah, she's here. Cool. This little triangle here is what we're going to be looking at, like Kyler said. And Cynthia, I would like you to attempt basically making the relationship between FA of X and FA of Y because of this triangle, which is 30 degrees. And I'm going to redraw the triangle for you. So basically, we've got our yoink, doink, doink. That's a bad triangle. There we go. That's a 90-degree angle. And because we can do this, this is also 30 degrees. And so if I draw a straight line here, I can say this is 30 degrees, which means I can say that this is 60 degrees. So here we have a 60 degree here. And we know that this is FA of Y, and this is FA of X, okay? So I would like you to write one of these in terms of the other. So what trig function would we use for that?
Would we use cosine?
Not quite.
Okay.
So here's the hypotenuse. Here's our opposite. And here's our adjacent. And we want to relate the opposite and the adjacent, okay? So
Okay.
which trig function looks at the opposite and the adjacent together?
For remembering what trig functions to use, I always remember SOHCAHTOA, which is
Yeah, I like it because it sounds like suck a toe. But SOHCAHTOA, which is, I guess, so is sine op hype. So SOHCAHTOA is basically, it's just a letter for each thing. So it's sine is opposite hypotenuse. So we've got, well, this is a lot of things to undo. So we've got sine opposite hypotenuse, ka is cosine adjacent hypotenuse, toa, which is tangent opposite adjacent.
So we would use oh, I'm sorry. Everyone's talking. My mom's tutoring right now, and so everyone's talking and I can't concentrate.
You're all good.
that's okay.
What?
The SOHCAHTOA, and we've got the OA here. So
I'm really not for sure.
That's totally chill. Trig is one of those things that is hard to get your head around at the beginning. So basically what we're going to do is we've got so ka toa, right? And here's the H, here's the O, and here's the A, okay? So we have
Mhm.
the O and we have the A, all right? But we
Okay.
don't have the H, all right?
Okay.
So if it has an H in it out of these three things here, we don't want it. So this has an H in it, so not that. This has an H in it, so not that. So this one, right?
Yeah.
And T in this means tan, okay? So tangent,
Okay.
okay? So
Yeah.
this one is, the top one is sine, the middle one is cosine, and the bottom one is tangent, okay?
Okay.
And then the two letters coming after those, these letters here, are the opposite hypotenuse, adjacent hypotenuse, opposite adjacent. So basically you want to choose the one that you have the things for, okay?
Okay.
In this case, we have the adjacent and the opposite. So we're going to use tangent. I'm going to undo a bunch of stuff. There we go. Which we have these two things here. So what we're going to do is we're going to write tangent of 60 degrees, right? Equals the opposite over the adjacent, which is FAY over FAX, right?
Okay.
Okay. So then we can just throw one on the other side. We're going to multiply them both by FA of X. So we can say FAX tangent 60 degrees equals FA of Y, okay?
Okay.
This is the important equation that we are going to need to finish the stuff up here. And I am going to do a big delete here because on a lot of stuff can rewrite that because I need to get some space. I don't know if I can, I haven't used Zoom's annotation stuff a lot, so I don't know how well it works for like selecting large quantities of things and then deleting them. Oh, there we go. FA of X times 3. Okay, so I'm going to rewrite it up here. So it was FAX tan 60 equals FAY. All right?
Yeah.
Okay, so can anyone tell me what we're going to do with that to be able to solve one of these equations? One of these variables, I guess. We have two equations that have FAX and FAY in them. It is our moment equation here, this one, and our little triangle relation equation down here, right? So what we're going to do is we're going to combine these equations. And the way we're going to do that is by substitution because we have something by itself over here, which is FAY. So basically what we're going to do is we're just going to, because these two things are equal, FAY is in this equation. So we're just going to kind of like put this in its place, okay? And what that's going to give us, and I really think I need to go to another sheet because I am really out of space here. But I'll write this one equation down here. So we got 1650, and I'm rewriting this equation up here, okay? 1650 minus what we're going to substitute is FA of Y. So we have FAX tangent 60, and then all of that times 12 because of this 12 up here, minus FAX times 3, and all of that equals 0. And now we only have one variable in this equation because those are the same thing. So we're going to go ahead and do it. So basically what we're gonna do is just try to get everything on one side, basically. So we can just, because this is a negative and this is a negative, we can throw those over to the other side by just adding them to both sides. And so what I'm just gonna do is say plus and equals is there. And this 0 goes away, okay? To save on some space here. There we go. So there we go.
You could probably just rewrite that equation on a new page and
Yeah, that's
solve
what
it
I think
there.
I'm gonna do. I think I'm gonna rewrite all these equations on a different page because I am thoroughly running out of space. Oh, the annotations a stay. That's great. Let's see if does the annotation menu have anything to like keep some stuff and delete other stuff,
Mm.
like a new page sort of thing. Clear, save, clear viewers drawings. No.
Is there an erase tool where you could just like erase some of the stuff?
Yeah, there is. I'm gonna have to do that. Oh wait, there's a save button. What does that do? Screen saved? Well, that's not very helpful. Okay. I was hoping that there was something that I could like do like a new page sort of thing, but I guess it doesn't like that idea. So I'm just gonna move this up here and then I'm gonna erase what's what I don't need. What the heck? Oh, yeah, don't save. There we go. All right. So annotate, erase, and we'll erase a whole loads of stuff. All of this. Yep, cool. Space. All right.
The final frontier.
Yeah, exactly. All right, so now what we're gonna do is we're gonna use a calculator because no one knows how to do tangent in their head. So trig tangent 60 equals like 1.7-ish times 12. And so now we have, make sure I'm on draw. There we go. We have 1650 equals 20.78 FA of x plus 3 FA of x. So we're going to add those together. So we're going to get 1650 equals 23.78 FA of x, which we can then divide both sides by 23.78. So we've got 1650 divided by that number. So we have 69.37 equals FA of x. Okie-doke. It was a road to get there, but does that make sense to everyone? Actually, better question. Are there questions? Because I hope there are.
Where does 1650 come from?
Yes, so the 1650 is from over here. I wrote that earlier, but I did erase it. It's basically taking this 150 times 3 and adding it to this 100 times 12, right? So 150 times 3 equals 450. And then 12 times 100 equals 1200. Add those together and we get 1650. Okay? So this whole thing up here is actually our moment equation. It's just been rewritten and changed a little bit. Okay? Does that make sense? Yes, no, maybe so.
Yeah, it does.
Alex?
Yes.
That's a very hesitant yes there. If you have questions, please ask them. I know this is a lot. This problem is harder. So like I definitely want people to be asking questions.
On a problem like this, there's like a lot more steps but all of the steps on their own are the same thing that we've
Yeah.
been doing. So
Basically, what every single step is going to boil down to is something like something equals 0 equals a bunch of other stuff. And that bunch of other stuff, individually, it's going to be like a force plus a force plus a force. If this is a force, then they'll all be forces, right? If it's a moment, then it's just going to be a force times a distance plus a force times a distance plus a force times a distance. And it's just, you're just going to repeat that thing over and over again. And you're going to end up with a bunch of equations. And then once you have a number of equations that is equal to or greater than your number of unknown variables, you're just going to start squishing those equations together, basically, until you can find what you're looking for.
one of the wackier steps was where he kind of like switched around some pluses and minuses and kind of magically
Yeah.
made it into
So
an equation.
that's true. That was algebra there. And actually, that's a good point. I should probably show kind of how that worked.
I mean, the easiest way to think about it when you're setting something equal to 0 is that all of the positives are going to equal all of the negatives. Like in the equation.
I would not say that. And the reason why is because, so in this particular equation, we had this, which is, so I'm just writing it out. There we go. Oh, that was a minus. I'll erase it. So we had the following. 1650 minus fa of x tangent 12, or tangent 60 times 12, minus fa of x times 3, right? So what I did was I added this to both sides, and then after that I added this to both sides, right? So if I add it, then like if I guess I'll write it out, plus fa of x tan 60 times 12, right? If I add those together, this whole thing, this block here equals 0, because it's the minus version of that times the plus version of it. So that equals 0. And then if I also add this to itself, right, then I get plus fa of x times 3. Those add up to 0. And then I have to add it on, I have to add both of those things to the other side as well. So I do plus fa of x tangent 60 times 12 plus fa of x times 3, and those get added to 0. So this side then becomes this, and these cancel out, right? So what I know that's real messy, but what we end up is we end up with what's below, which is 1650 equals the positive versions of these. And the reason I disagreed with Kyler is because when you're doing an equation, you're not looking for the minuses and the positives against each other. You're looking for a variable. So like, and this is purely example, it has nothing to do with this problem. But if I had 10 minus 5 plus, I don't know, x minus x, or I guess x times 2, doesn't really matter, all equals 0. If I were to say 10 plus x equals 5 plus x times 2, that would be taking the minuses here, and I'd be putting them on the other side. That's fine. But in the end, I don't really.
Useless there.
Yeah, that's pretty useless. It's basically the same as what was above. So what I want to do instead is keep all the x's on one side and keep all the numbers on the other side. So what I'd be doing here is I'd be subtracting x from both sides. So I will rewrite it, 10 minus 5, and then this plus, or this minus x is 0. So we just won't write it. And then so x times 2. And then I'd be subtracting it from this side as well, so minus x. And then I'd add this to both sides. So I'd be 10 minus 5 equals negative x plus 2x. And then what I can do from there is just combine the things on both sides, right? So then I can just say 5, because 10 minus 5 is 5, equals x, because 2x minus 1x is x, and then I know that x equals 5, right? So I'm separating the variables out. And that's what I'm doing that whole time, is just trying to get the variables alone so that I can find out what they are. Does that make sense to everyone? Or is there any questions with that? Any questions at all? I find it hard to believe that there are none, but okay. Does anyone have any questions about the just what we did here so far? Please ask questions if you have them. The hard thing is that me instructing this class, I assume that there are probably questions, but I don't know if you have questions, and I don't want to just sit here and wait on a question that you don't need the answer to. But if you do have questions, I need to be able to answer them, because the whole point of this is to learn. So if you have a question, please do not be afraid to ask it. No one in this class knows what's going on. I don't even know what's going on. So feel free. All right, well, I'm going to take that silence as a no, David, you're worrying too much. Stop asking if we have questions. All right. Hopefully you guys have this written down, because I have to erase it for space. I'm also going to erase this bottom one because we don't need it anymore. The important bit that we have now is just this answer here, okay? So can somebody tell me what we're going to do with this answer to find our next variable?
You can multiply that by tangent of 60 to find fa of y.
Yep, so I can plug it into this equation down here. So I can say 69.37 times tangent of 60 equals fa of y, which equals something, which we're going to find out here in a sec. Trig 60, there we go. Which equals 120.16. Okay. Dope. Look at that. We have two variables. So I'm going to write them up here. 69.37 equals fa of x, and 120.16 equals fa of y. And then I'm going to erase these because it's a bunch of space. All right, cool. And I'm going to keep our equations over here because they're still useful, obviously. So what am I going to find next? Using these.
Now you can find fb of y if you move 360 and fa of y
Yes.
to the
So,
other side of the equal sign.
yeah, and actually for explanation's sake and algebra's sake, I'm going to go ahead and do those out so that you guys can follow along. So rewriting this equation here, we have fa of y plus fb of y minus 360 equals 0, okay? I'm going to take this up here, this fa of y that we found, and I'm going to plug it in, put it into that spot. So I now have 120.16 plus fb of y minus 360 equals 0. I am now going to add 360 to both sides. So we'll just do plus 360 and plus 360. And what that gives me is 120.16 plus fb of y equals 360, because these sum up to 0. And this sums up to 360. And then I'm going to subtract this from both sides. So minus 120.16 plus, or nope, there we go, minus 120.16. So that's going to give me fb of y equals 360 minus that, 239.84. There we go. So that is our answer for FB of y. Does that make sense to everyone? Kind of written out this way?
Yeah.
Yeah.
Does anyone have any questions on how this works or how any of this works, I guess?
How did we get to 39 .84?
Yeah, so 239.84. That is 360 minus 120.16. So this here, basically, if I did 360, 120.16, we'll do it this, and then minus. If we did this out, it would equal 239.84. Okay.
Yeah, that makes more sense now.
Okay. And yeah, these ones, when we add these together, they just equal 0. When we add these together, they equal 0. And 0 plus 360 is 360. That's how this goes here. Okay. So any other questions?
Cynthia, one thing that I don't know if you've like seen this happen before, but you can add the same thing to both sides of an equation and that doesn't change the equation.
Yeah.
So that's just what he's doing there.
So anytime, yeah. Basically, if I have like 10 plus 5 equals, I don't know, well, I can't do that, equals x. If I
I mean, you could even just do like 10 plus 5 equals 9 plus 6.
yeah, that works too. But what I'm going to do is this. Say I want to know what x is. If x were 15, right? 15 minus 5 equals 10, right? Does that make sense? So if x was 15, 15 minus 5 equals 10, right? So if I did this, I could then instead just add 5 to both sides, plus 5 plus 5. And that gives me 15 equals 15, which is correct. So assuming that here, basically just if I add 5 to both sides, the same way I did down here, so plus 5, then I get 15 equals x. So if you add the same thing to both sides of an equation, the equation stays the same. You're just kind of like reformatting it, rearranging it. And that's basically the basis of all algebra, is just moving things around to try to make something make sense.
Okay.
So that's what we're doing here. And also here. Basically just rearranging, pushing numbers to other sides so that we can singles. So I'm going to erase some stuff, and then we'll write 239.84 equals FB of y. Yeah, that's right. I'm going to erase all this. So we have another variable, which is very, very good. And we have one more variable to find. So how do we find it?
Subtract FA of x from 150.
So we're basically going to do the exact same thing that we did with this equation, like what we just did, but with the other equation, which is the x equation. So we have, well, I'll write it all out again. FA of x plus FB of x minus 150 equals 0. So then we can plug in our FA of x, which is 69.37, plus FB of x, minus 150 equals 0. We're going to add 150 to both sides. So then we get 69.37 plus FB, that was a B, FB of X. And then this adds up to 0. So equals 150. There you go. And we're going to subtract 69.37 from both sides. This adds up to 0. So we're going to have FB of X equals whatever that is, which is 150 minus this. So 80.63. Yes. So we now have our last bit, 80.63 equals FB of X. And is everyone cool if I erase this?
Yes.
This will all be on the recap video. I am still, I'm recording right now, so if you do need to go and look back at equations, you definitely can. Okey-doke, cool. And I'm gonna leave those because those are our original equations. This one's not. All right. So now that we have that, we're gonna look at our original problem again. We're just gonna pull it in. And I wonder if I can move things because that's gross looking. Select. Yeah. Is it janky? Yes, it is. Okay, so now we have all of these, and I did have to erase kind of our free body diagram, but I can redraw it real quick. Basically, we have a force here, we got a force here. That's FB of X, that's FB of Y, this one. And then we have our FA, and it's split up into its components, FA of Y, and its component FA of X. All right, so we have found all of the component forces. Normally, we would take our FA of X and FA of Y over here, and we would use them to find out what FA is. Because this force that's being applied is not actually in components, it's being applied at an angle. And we know that it's at a 60-degree angle. So we would instead say like FA at a 60-degree angle. However, we're basically out of time for this class period, so I'm not going to have us do that. We're just going to leave it in its FA of X and FA of Y components. But typically, we should simplify this into just FA. And the way we would do that is through trigonometry. So, or just triangles, it doesn't really matter. Basically, we'd be saying, I don't know, let's choose one. Let's choose FA of
You
Y.
can basically just use the same equation that
Yeah,
FA,
exactly.
well, not quite.
Not quite, but basically we'd say this is 60 degrees, this is this number. So we'd say we want basically FA, which is the hypotenuse. So we could say that sine 60 equals 120.16 over FA. We can multiply both sides by FA and then divide both sides by sine 60. And what we end up is FA would equal 120.16 divided by sine 60. So that is the answer. I guess I'll just do it real quick since it's not that hard. Divided by trig sine 60. So we know that FA equals 138.74. So that's how you do it. I did it real quick just because we are out of time. But so I know that's a ton of stuff. For the day. Hopefully everyone got through it okay. The recap video will be posted. I encourage you to please go watch that recap video if you need to refresh anything, practice anything. The homework is going to be coming out soon. And one of the things with that is I'm going to start using Google Classroom, which means I'm going to need either people's emails or I'm going to need you to go to Google Classroom and sign up with my class code, which I will put that out. I'm going to put the class code out on the Discord and the resources. Another quick sort of reminder, or yeah, I guess it's a reminder. In the Discord channel, there is a thing, one of our text channels that says MEC Q&A. That is for questions. So if you guys got questions, just throw them in the Q&A channel. The resources channel and the other channels are more for like me to send you things. So try to use the Q&A if you have questions on the Discord. I will send in the resources channel the class code for Google Classrooms, meaning if you want to, you can go to Google Classrooms, make a student account, and then with your Gmail or your email, I guess, and then type in that class code to join my class. Or if you don't want to do that, you can send me your Gmail, whatever you use for Google Drive, Google, all that stuff. Send me that and I will add you. Either way works for me, but it's up to you. Okay. Does anyone have any questions on any of that?
None here.
Okay. Go ahead, Cynthia.
No, I don't have any questions.
Important thing, I'm going to start putting the homeworks out on Google Classroom. I won't be posting them to the Discord because I want you guys to be using Google Classroom because 1, it auto grades for me, and 2, I can give it a due date, and that due date is going to be Monday because I did have some people give me their homeworks 10 minutes before class, and that makes grading a pain. So the due date's going to be Monday, meaning you'll have to turn it in before Monday. Okay. So yeah. Oh, also on homeworks, please show your work. Some did, some didn't, but please make sure to show your work. That way, if you do go wrong somewhere, I can see where you went wrong with it, so I know what to go over. So yeah. If that's cool with everyone, that is class for today. Unless anyone has any questions, I'll stay on for a sec, but you guys are free to go.
Okay, thank you for class.
Yep.
Bye.
Adios.
Bye.
All right. Bye.
Bye.